A sample of sodium metal with binding energy, which is also called work function, of 2.2 electron volts. What is the maximum possible speed of a released electron if the wavelength of the light is 500? Okay, so we've got a few steps to do here. We're going to use the E photon equals binding energy or work function plus Ke max. And so we can get Ke max is E photon minus the binding energy, because we know we're asked for speed. Speed we know is going to be, or hopefully we can think of it as, remember that it's in kinetic energy, it's related to speed, right? So 1/2 mv squared. So if you get the kinetic energy, then we can get the speed. But we're talking about binding energy and stuff, and this is about the only equation we have with binding energy, so we'll do that first. So Ke max, we also have wavelength instead of E photon, and so we can use the 1240 eV, yeah, we'll go with that, nanometers over lambda minus Be to get Ke max. We're going to have to convert it into joules because this is going to be electron volts, but that's okay. So we got Ke max is going to be 1240 eV times nanometers divided by our wavelength, 500 nanometers. The nanometers are going to cancel. We're going to get eV, but then we got to subtract off the binding energy. This is 2.24 eV. So 1240 divided by 500, and then subtract off 2.24, and we get 0.24. Yep, okay. Is Ke max, but we want it in joules, so we can do 1/2 mv squared and get velocity in meters per second, all standard kind of stuff. So 1 eV is 1.602 10 to the negative 19 joules. And so our Ke max in joules is 0.24 times 1.602 negative 19. 38 point, we'll just keep one extra sig fig for a minute. 38.45 10 to the negative 21 joules. 21. All right, so we're going to use that is equal to, so Ke max is 1/2 mv max squared. So V max takes divide through by 1/2 Ke divide through by 1/2 m, and then take the square root. So we got Ke max over 1/2 m. In this case, that's going to be square root of 38.45 10 to the negative 21 joules over the 1/2, 0.5 times mass. We're talking about electrons, so 9.11 10 to the negative 31 kilograms. Kind of running out of room here, but I think it'll work. Square root of 38.45 negative 21 divided by 0.5 times 9.11 e negative 31. Looks like 291 times 10 to the third meters per second equals V max. Let's see if that's what I got last time. Something like that. All right. Somehow I had 290, but we'll go with it. What is the minimum frequency of light that can cause electrons to be emitted from the sodium? Minimum frequency. All right, so we're going to do E photon is equal to binding energy plus Ke max. When we want to put in the minimum energy from our photon, we're going to let there be no extra kinetic energy. So all it's going to be is binding energy. So it's going to get out and just going to be stuck sitting there, no speed, just barely got out, and that's how we can figure out the minimum frequency. And so one equation for the photon energy is h times the frequency, Planck's constant times the frequency, and if that, then that's equal to the binding energy. But we're going to want this in joules because this is h is in joule seconds, and this is 1 over seconds, and so let's change this to joules. 1 electron volt is 1.602 10 to the negative 19 joules. So the electron volts cancel, we'll end up with joules. (358.8) 10 to the negative 21 joules equals h, Planck's constant, 6.626 10 to the negative 34 joules times seconds times F. So F is 358.8 10 to the negative 21 divided by 6.626 10 to the negative 34. So F is plugging that in, and I get 542 10 to the 12th hertz. 1 over seconds is hertz. Okay, looks good. If a half a milliwatt laser is used to shine light on the sample, how many electrons are released per second? All right, so this is watts. A watt is a joule per second, so we got 0.5 times 10 to the negative 3 joules every second are sent in. To get each electron, though, each electron has to have a photon. And each photon, did I calculate the energy of a photon in joules? Okay. We're going to have to know the wavelength. We'll assume that we're using the 500 nanometer wavelength like we're using up here. And so we can get the energy of each photon, which we never did calculate exactly. We just did. So let's go ahead and calculate the energy of a photon of 500 nanometer light. And so E photon is going to be hc over lambda, and let's just do it in regular units so we get joules. So H is 6.626 10 to negative 34 joules times seconds. C is 3 times 10 to the 8th meters per second, so the seconds are gone. And then we will divide by the lambda, which is 500 10 to the negative 9 meters. The meters are gone, and we end up with joules. Yes. Okay, so E photon is 6.626 E negative 34 times 3E8 divided by 500 E negative 9. So the energy of one of these photons is 397.6 10 to the negative 21 joules. Okay, and so that is how much we need for each, how many joules we need for each electron. So let's just divide here by 397.6 times 10 to the negative 21 joules per electron. And so we're going to get, when we divide this, the joules are going to cancel, and we're going to have, this says electron. And so when we divide fractions, we flip over and multiply, so this will be electrons per second is what we'll end up with. Electrons per second. And so let's just put those numbers in. 0.5 e negative 3 divided by 397.6 x times 10 to the negative, lost my 1 there, 21, negative 21. So I get 1.26 times 10 to the 15th electrons per second. How many electrons are released per second? Okay, that should do it. What is the stopping potential for this sodium metal? Remember the stopping potential, if we took the work function is equal to the stopping potential times the charge of an electron, and in electron volts this just goes away, and so then it's just, we can just basically the value of the binding energy in electron volts is also the voltage. So V equals 2.24 volts, because we got 2.24 electron volts equals V naught times the charge of an electron, so we can think of it as electron charge cancels out. So however you want to look at it, the stopping potential number wise is equal to the binding energy in electron volts. Units are different, but we can get the number that way.